Welcome back to CS520. In this session I'm going to talk about translating vm520 branches to Intel 64. What's the problem? The problem is that Intel 64 instructions are variable length. Therefore, there's no simple formula to derive Intel address from a vm520 address. In general, this means we need to make one pass through the vm520 code and build a table that maps vm520 addresses to Intel 64 addresses. Then we can go back through the translated code and fill in any holes. The problem's with forward branches, if you think about it. We're branching forward into the program, and we haven't yet decided how much Intel code is going to fill up that gap. We know how many vm520 words there are, but since the Intel instructions are variable length, we're not quite sure, because it depends on the vm520 instructions that are translated. We're not quite sure how many Intel bytes there's going to be skipped over. So we'll do this by looking at an example. This is an example that just codes up a simple if then else. And let's walk through it real quickly. Like all of our vm520 programs that we're going to translate to Intel code, it starts with a jump instruction. In this case, it's jumping +3. And this is found at vm520 address 0. And right now, we haven't generated any code for Intel 64, so it's also 0. And we know how to do this, right? We're going to translate this into an Intel jump E9. The +3 says it's got to jump over 3 data words. So that's going to be 24 bytes because each data word is 8. And we have to add 3 for the padding that we're going to put on the end of this jump instruction. So that means we're going to jump 27 bytes in the encode. So I just have to encode that 4-byte offset. 1B for the decimal value 27. And then, like we always do, we pad that instruction out with 3 0 bytes just to keep everything on quad word boundaries through the data section. Next three words are just data words. They just get expanded into quad words. In this case, they're all positive numbers, so we all have 0 bits that are being added. Down here, then, we start the actual instructions. In the vm520 code, we have a load. The load offset is -3. Remember, the PC will be actually 5 at the time the load is executing. So we add the -3 to the 5, and that tells us that we're going to be loading from address 2, which would be up here, this data word. Okay. In the Intel code, then, it's going to be a move quad word. The second data word is at offset 16. We know that RDI points to the base of the code. So we're just adding the offset of the second data word, 16, to the RDI, the base address of the code, and moving the word at that location to R8. That's the equivalent of doing the load in vm520. And it's a backwards reference into the data words, so we know at this point, we know how to translate that address. Basically, it's just multiply it by 8. Right? Similarly, we have another load instruction, same story. Offset again is -3, but now the PC will be 6 at the time this executes, so that means we're going to address 3, so it's the same exact situation, just the offset applied to RDI is 24, because address 3, the Intel address, is 24. Okay, so that's all straightforward. Let's keep going. Now, the next instruction we see in the Intel code is a branch greater than. It compares these two registers and is branching +2. Again, the instructions at location 6 in a VM machine. The PC therefore will be 7. We'll be applying the +2 to the 7, giving us that the branch destination is actually address 9. The problem is we don't know where address 9 is going to be yet. Right, and we can't unlike data words, we can't just multiply it by 8 because the instructions are variable length. Let's just go back and look at some of these instructions we've already generated, right? These move instructions here, move quad word instructions, are 7 bytes long. So the problem is we don't have a simple formula, so we're going to have to just wait and see. But we know what kind of instruction we want to generate. Right? We know we want to generate a compare instruction to compare the two registers. That's going to be done with these 3 bytes, and there's nothing to be wondered about there. We know what registers we're going to compare now, and we can compare them. The problem is in the Intel machine, it's going to take us 2 instructions because we have to do a compare instruction followed by a jump greater than instruction. Jump greater than instruction has a 2-byte opcode actually, followed by a 4-byte offset. But right now we don't know what these offsets are going to be, so we have to just leave a hole in the code. But we know how big the offset will be. We've allocated 4 bytes, so we can keep generating addresses. Even though we don't know what to put in these boxes, we can generate the address of the next instruction because there's 1, 2, 3, 4, 5 plus 4 is 9. So we add 9 to the address of this instruction to get the address of the next instruction, even though there's a hole to be filled in. Okay? So we'll just keep going, leaving the hole and remembering to come back and do it later once we know where address 9 actually is in the Intel world. Load immediate instruction, nothing very interesting here. We know how to encode that. We go ahead and encode it. We update our counter. Move quad word will take 7 bytes, so that increases the Intel address to 62. At this point, we find a jump instruction with a +1 address. Again, the jump instruction itself is at address 8. So the PC will be 9, which means that we're adding 1 to 9 to get the destination address of the jump is going to be 10. Again, we don't know yet where address 10 is going to be, so we're going to have to generate a jump instruction, which as we know is E9 with a 4-byte offset. And again, we just have to leave it as a hole to be filled in later. But again, we know how many bytes this instruction will take up. It's going to be 5. So we update our Intel address. The address of the next instruction is going to be 67. VM instruction at that location is load immediate R211. So again, straightforward implementation of that. Just move quadword.R11 into register R10. We know how to encode that. We can update, again, that's a 7-byte instruction, so we can update the Intel address. We know the address of the next instruction is going to be 74. This is a store instruction in the VM machine. R2 with a -10 offset. Instructions are located at address 10, so the PC will be 11 when the store actually executes. -10 plus 11 gives us an address of 1. This is back in the data section, so we do know the address of that again. We know we just want to encode that as 8, an offset of 8, which is the 1 times 8 off of our IDI register, which points to the base of the code. And again, we know how to encode that. Okay. Finally, the last instruction is our halt, all zeros. We know how to generate a return, which is C3, and we know the address for that now. Okay. So now we can go back and fill in the holes. We go up to this hole here. We know we wanted to jump to address 10 in the VM machine. So we can look through our table now and see address 10. Address 10 in vm520, we now know is actually address 74 in the Intel machine. Okay, and what's the PC going to be? PC is going to be pointing to the next instruction at the time that this Intel jump instruction executes. So it's going to be 67. So the PC will be 67. So that means we want an offset of 7 in order to advance to 74. Okay. So in fact, we wanted in here a jump to +7. And we can go ahead and fill in now. We can go ahead and fill in this code, right? 07000000. Okay, once we've generated all the code, then we know where all the addresses are in the Intel machine, and we can go in and fill in holes. Okay, so this was sort of a hole we had to figure out. Once we figured it out, then we know how to encode it. Similarly, we can go back to here. This was doing a jump to destination address in a VM machine, vm520 machine of 9. We now know the 9, right? vm520 address, vm520 address 9 is Intel address 9 is 67. Okay, so the destination address is 67. What's the PC going to be? Well, it's going to be pointing to the next instruction, which is 55. So how do we advance 55? We're going to have to add 12 to it to get 67. Okay. So, in fact, this jump greater than instruction in the Intel is going to need a offset of plus 12. So we know now how to fill in this hole. 0C, 00, 00, 00. Okay. So that's the task at hand when you're generating, when you're translating VM branch instructions to Intel branch instructions. If it's a forward jump like we had in this example, you're going to have to wait, leave a hole, and when you get done with the first pass over the code, you can go back and fill in those holes. So what you might want to do in your translator is build the translated code into the buffer, and then you're basically skipping over these holes. But you're going to have to keep a data structure that remembers where the holes are, and then you can go back and fill them in. I mean, alternatively, you can make 2 passes over the vm520 code and just build a data structure that keeps track of the vm520 address and the Intel address. So the first pass, you don't generate any code actually. You just go through and figure out where the addresses are. How long the code is going to be in the Intel for each one of the instructions in vm520. And you can build then this mapping, the data structure that maps vm520 address to Intel 64 address. Then you can go back, read the vm520 object code again, and now you'll know everything you need to know to just go ahead and generate the instructions. You won't need to leave any holes. You can just fill it in. What this should remind you of is our discussion earlier in the semester about assemblers. Right? The assemblers have a similar problem with forward references. They don't know how much code there's going to be, so they have to wait until the code has actually been visited once, read once, and then they can go back on a second pass and fill in the branch destinations. They're forward branches. Okay, let's stop here.